Surface tension arises due to molecular force of attraction. Surface tension arises due to molecular force of attraction. So, we have to understand molecular force. Molecular force exists between two molecules. If the molecules are of same material or same substance, the force is called cohesive force. If the molecules are different, then it is called adhesive force. For example, if a glass rod is dipped in water, forces exist between glass molecules and water molecules. These forces are adhesive forces. The force between water molecules and glass molecules is adhesive force. Forces exist between water molecules. This force is cohesive force. The force between water molecules is cohesive force. The force between water molecule and glass molecule is called adhesive force. Like this, two types of forces exist between molecules. These forces, molecular forces, are short-range forces. They will be confined to a sphere of influence. They arise due to electric fields. Molecular forces arise due to electric fields. Their influence is over a small region, so they are called as short-range forces. Moreover, we imagine a sphere up to which these forces act, that is called sphere of influence. Sphere of influence. To understand the sphere of influence, we have to understand the radius of the molecule. The molecule will be of radius 10 to the power of minus 9 meters. Approximate radius of a molecule is 10 to the power of minus 9 meters. We imagine a sphere with this radius around a molecule, and this we imagine to be the sphere of influence. The sphere of influence. So the molecules which are situated at this distance, they influence the molecule. Hence, we take this sphere as the sphere of influence. To understand this, to picturize this, see the figure. In the figure, you notice small circles. There is one central circle that represents the molecule which is under consideration, and the circles around it are the molecules which influence this molecule, and the bigger circle represents the sphere of influence. Like this, we have to imagine. This molecular force of attraction is a two-way force. It is not a single force. So it acts on both the molecules. Molecular theory of surface tension. To understand this, let us take the figure. Imagine that figure as though it is a trough containing some liquid, and the circles A, B, C, D, E represent 5 molecules. The molecule A is completely inside the liquid. The molecule B is in the surface of the liquid with more than half inside the liquid. The molecule C is also in the surface of the liquid with half inside, half outside. And molecule D is inside the liquid, inside the surface, with less than half inside, and E is the molecule which is completely above the surface of the liquid. Like this, imagine 5 molecules. Now let us try to understand the forces acting on these molecules. Equal and opposite forces act on A, which is completely inside. So the net force acting on A will be 0. Consider the molecule B. More than half is inside. Hence, more downward force acts on this molecule. There will be a net downward component of force on this molecule, because there are no molecules over the upper part which is outside the liquid. Hence, there will be a net downward force into the liquid. Similarly, on D also there will be a net downward force into the liquid. And C is half inside and half outside. So on C also there will be a downward force. The downward force on C is maximum, though there will be downward forces on B, C, D. Though downward force acts on B, C, D, the downward force, net downward force is maximum on C, and it is less on B and D. There will be no molecular force of attraction on E. Like this, we have to understand the molecular force of attraction on several molecules. The molecules inside the surface of the liquid, will have more energy. To understand this, let us imagine a molecule coming into the surface of the liquid. While coming into the surface of the liquid, it has to overcome the molecular force of attraction, the downward force of attraction by the molecules. Hence, it should possess more energy compared to the molecules inside the liquid. So, the molecules situated in the surface of the liquid will have more energy. Due to this energy, the surface takes a spherical shape. Due to this energy, the surface takes a spherical shape. Due to the surface energy, the surface of a liquid takes a spherical shape. Since the energy of system, the energy tries to attain minimum surface area, the surface of a liquid takes a spherical shape. This energy is potential energy. Hence, potential energy per unit area of the surface is called as surface energy. We can take it as the measure of surface tension. It can also be defined, that is, surface tension can also be defined as the amount of energy required to increase the area by unity. The energy required to increase the area of the liquid, surface area of the liquid by unity, can be taken as the definition of surface tension. We can prove that the surface energy per unit area is equal to surface tension. We can prove that the surface energy per unit area is equal to surface tension. To derive this relation, to show this, let us consider the figure. In the figure, ACDB is a rectangular metallic frame bent in the shape of U. P1, Q1 is a rod, and mg is the weight attached to this rod. This rod is pulled down by an amount x to the position PQ, and in this position also the rod will be in equilibrium. Like this we have to imagine. So ACDB is a metallic frame. P1, Q1 and PQ are two positions of a rod, and mg is the load attached to this rod so that the rod is in equilibrium, and the rod is slowly pulled down by an amount x so that it is in equilibrium in both the positions P1, Q1 and PQ. Like this we imagine this figure. Let us consider the length of the rod PQ as L. Since soap film will have two surfaces, the total length over which the surface tension force acts is 2L. If we suppose that the surface tension is T, if you take the surface tension as T, then the force acting over length 2L is 2LT. The force acting over a length 2L is 2LT. By moving the rod by a distance x, in moving the rod by a distance x, the work done is force into displacement 2LT into x. Thereby, the increase in area, the newly formed area is 2L into x. 2L is length, x is breadth, 2L into x is the area formed. Hence, the energy per unit area is 2LTx by 2Lx, which is equal to T. 2LTx is the energy used and 2Lx is the area formed. Hence, 2LTx by 2Lx is equal to T. So, the surface tension can be taken as energy per unit area. See the right side figure. We have to imagine it as though a beaker containing water. The red cylindrical one represents the beaker containing water, and inside this beaker, inside the water, the vertical cylinder represents a capillary tube, glass tube, a glass tube dipped in water. Near the surface of water, we notice the water column rising along the capillary tube. The water column rises along the capillary tube, thereby forming a curved surface near the surface of the glass tube. Draw a curve along the rise, a curved surface. The curved surface is drawn with a line. The curved surface is drawn with a line, and a tangent is drawn to this curved surface. A tangent is drawn to this curved surface. The angle between this tangent and the surface of the solid, the surface of the capillary tube inside the liquid, this is called angle of contact indicated by theta. This is angle of contact indicated by theta. By observation, we notice that this is an acute angle. It is less than 90 degrees. Angle of contact in mercury. In a trough, if mercury is taken, mercury is taken and a capillary tube is dipped in mercury. If a capillary tube is dipped in mercury, then the mercury level falls inside the capillary tube and around it. Inside the capillary tube and around it. If you draw a curve, I have shown a white curve which represents the curved surface, and to this curve a tangent is drawn. This is the tangent to the curved surface of the liquid. This is the tangent to the curved surface of the liquid. Now, the angle made by this tangent with the surface of the solid, that is with the capillary tube, it is known as angle of contact. Angle of contact. This is greater than 90 degrees. This is obtuse angle. The angle of contact depends on adhesive forces and cohesive forces. The angle of contact theta is less than 90. The angle of contact theta is less than 90 if adhesive forces are greater than cohesive forces. If adhesive forces are greater than cohesive forces, then the angle of contact is less than 90. And in such a case, the liquid rises in the capillary tube. The liquid rises into the capillary tube. If such a liquid is placed on a glass plate, then it spreads over the glass plate. The angle of contact will be greater than 90 degrees. It is greater than 90 degrees if adhesive forces are less than compared to cohesive forces. If adhesive forces are less than cohesive forces and the liquid column falls inside the capillary tube. If such a liquid is placed on a glass plate, then globules are formed. Small droplets of liquid will be formed on a glass plate. Globules are formed if such a liquid is placed on a glass plate.